Okay, haven't found time to kind of briefly explain how I use Canvas. Calculus does not, in my opinion, it doesn't work very well as an online class. If you want to take it as an online class, there are options like BYU Independent Study, that sort of a thing, but it's not what I'm doing. Like last year when we had to do a lot of online things, it just didn't work that well. So I highly encourage you, if at all possible, to be here. Sometimes you don't have a choice, and I understand that. So what I use Canvas for is just a way to keep track if you're on pace. So most of you have figured that out. You just go into Canvas. I just have a list. You just work your way down the list. It's usually just videos and certifying homework. So you click on the video link. It simply says, tell me that you were either in class or if you weren't, that you studied the video. And then that just dumps into Skyward so I can keep track that you're staying with me. Same thing on the homework. I run the class on the honor system. If you are dishonest about your homework, it will become painfully obvious that you were when you get a test score of 37 out of 100. Okay? That is not exaggerating. Those are real scores. Okay? So anyway, make sure you're keeping up with Canvas. The dates in Canvas don't always make that much sense. So someone asks, can I use the calendar? I'm like, not really. It doesn't really match up with the class very well. That's because Canvas makes it difficult for me to make due dates that are like for A day and for B day and for first period and fourth period. It's way too much. So I apologize that I'm not going to do that to make the calendar useful. What I do instead is if you need something that hopefully is easy for you to just look at and stay on pace, I just make a list. It's right here under homework summary. Someday it will open. There we go. And I just show the different packets I've handed you. It lists exactly what day I handed it to you and what day I expected you to bring it back finished. Okay. But if you're coming to class every day, it's really easy because I just hand you the packet and I say bring it back the next time. So, questions? Okay. I told you today, send out a couple of text messages, that I would pay you 5 extra credit tickets if you were 100% current in Skyward as of today. So I'm going to walk through them and do that. If for some reason, I don't know, like your text reminder still isn't working and you've got to get that fixed, if there's a valid reason why you're losing out on these 5 points, please come talk to me. I'm not trying to penalize anyone, but I am trying to make sure you do not fall behind. Look up. Everyone's looking. Okay, here's the key. We are going to take the first test, the only test for this term, on Monday, September 27th. You can write that down. We are going to take the first test. It is 80% of your Term 1 grade on Monday, the 27th of September. You will understand how seriously I consider tests in this class when you come to class that day, because you'll see that the desk will be completely rearranged. Totally new seating arrangement. You simply pick a spot. There's no required seating. The dividers will be on every single table. I'll be giving out alternate tests to adjacent tables because I have to get a very reliable measurement of how well you're doing. Okay? Now remember, you do not automatically qualify for a retake in this class. You only qualify for a retake if you're not falling behind in homework. So if you're behind in homework today and you continue to be behind, when you get a bad test score, the answer is going to be you kind of got what you planned on getting. Like you just did. Like you didn't stay caught up in your homework, so of course your test score is bad. And then you don't get to retake. It's the end of the story. You just have to learn to suffer the consequences of that poor planning. Now, if you are with me, like all of you have been very good at being with me during class. You're not on your cell phone, you're paying attention, you're focused during the discussion. If you're with me and you're also keeping up with your homework, then if you do not get a very good test score, all we do is we schedule some before and after school times when we can get together and find out why. Like, I've just got to get you to open up and talk about it. Like, why did you choose this answer? There's a reason you chose it. If you'll tell me why you chose it, I can help you understand why it's incorrect and help you prepare for a different, totally separate retake test. If you do better on the retake, we forget that the first test ever happened. Questions about the test? Please, Luke.
Are there any study how are we going to
So, no, good question, Luke. So you are all building your study guide. That's what we've been doing day by day. That's why you've got to make sure you have very good notes. You got to have good homework so you have something to study, something to reference. I have to get your mind away from the idea of a practice test, because the trouble is when I give you a practice test, everyone thinks, got it. If I can do the practice test, I can do the real. No, you can't have a mindset of if I can do it, I've got it. That's not how this works. You're not trying to do your homework. You're trying to say, do I understand the homework? Does it make sense to me? Do I get the why of each step? That's what you got to focus on. So we'll do some things to help you prepare, but you don't want to think of it as a practice test. So, questions? Please, Michael. No. So this first test, half of the AP test is multiple choice. Half of the AP, Michael Franson, right? Half of the AP test is multiple choice, half is written. What has worked really well for many, many years is I start the year doing multiple choice testing, because it actually is the harder part of the AP test, is the multiple choice. So this first test is 25 questions. Every single one of them is from an old AP test, I believe. And it's all or nothing. So you get the question right, you get the points associated with that question. If you get it wrong, you lose all those points. Does that answer your question? Yep. And don't be deceived with the idea of multiple choice. The story I always tell is of the student who, unfortunately, when he asked about the test and I said multiple choice, he got this very, how would you say, like, cocky look on his face. Yes. Arrogance is a better description. And I could just see his brain saying, yeah, multiple choice. Like, how hard can it be? When the AP test writers create multiple choice questions, here's what they do. They write the question. And then they sit in a group and say, okay, you all know how students think. What's one of the mistakes a student will make? And somebody says, they'll do this. Got it. Let's write an answer that matches that error. So, yeah, Katie gets it. When you're taking one of those tests, if you are thinking that error, you think you circled the right answer. Okay? It's not like a driver's ed test that's like, when you pull up to a crosswalk, what do you do? A, honk. B, run over the pedestrian. C, turn off the car and walk away. D, wait patiently while the pedestrian crosses the street. Like, you don't have to even study anything to know that. Just, okay. Look, the AP tests are, every single wrong answer is a trap. They're designed to get you to pick it because you think you're thinking correctly. Yeah, so, don't count on the multiple choice being easy in any way, shape, or form. The key is what I've been saying since the class began. Okay, all of you are doing one of the keys correctly. You're here, you're participating in the discussion, you're very focused, okay? And you're very focused on, I can tell by your questions, you're very focused on understanding, not doing. That's key number one, you're doing really well at that. Key number two is to make sure that when you do your homework, you're not doing the homework. You're thinking of it as, did I really understand what this question even asked? Like, do I get it? And I've had people in after school and before school who you can tell that's what they're struggling with a bit, and their questions are really helping. That's all you got to do. If you do that, you'll be well prepared. So, questions? Cool. Okay. So let me pay real quick. So I did check Skyward, so I have a list of those who don't have 100%, but I would prefer that you just tell me. It's a lot easier than me looking at my list. So when I come by your desk, you get 2 points if you have the green packet finished. That's homework. and you get 5 additional tickets if you are at 100% in Skyward as of right now. So, Michelle. Okay, do you have the homework done? Still catching up. You're okay. You do. Do you have the homework done? Good work. You are. No, you are, Payson. Katie?
I think I have 100.
You are, yes. Homework done? Good work. Maddie?
I have the homework done.
Yep, you are 100% as well. Anna? I concur. Good work. Ben AC, you guys switched up the seats today. Trying to trick me, man. Trying to trick me. I don't memorize by location. I memorize by face. So, everything done? Good work. Shoot, Simmons. Parker, yeah? Good job, Parker. Luke? Homework done?
Oh, yeah.
Excellent. Taryn? Good job. Question done? Good man. Finished homework? Good job, Spencer. Nice job catching up after the week away. Good work. Yeah, good work. Harrison? Excellent. Riley Barrett? Good job. Rachel, done with homework? Good job. Saw you were 100%. Good work. Chris, done with homework?
Yeah.
Saw that you were also 100%. Dallin? Fair enough. Good work.
I'm not really sure.
Yeah, you're not quite there. You're missing a couple of things. So you just got to go back and check and see what you're missing. So
Do I just like
it's just Canvas. Yeah, you just go, like really what I would do is just look at Skyward for anything that's missing, and then you just go to Canvas and see, oh, did I forget to certify the video, or did I forget to certify the homework? That's all. Does that make sense? You are. Good work. Amelia. Homework done? Good job. Hannah? Yep. Mr. Irwin. You actually do.
I do?
And did you get the homework done?
I did get the homework done.
Nicely done. Yeah, you're good. Good job, Soraya. Good job, Nate Ashton. Yes?
Yeah.
Haley. Good work. I gotta go get some more.
I'm caught up in Canvas, but I don't have.
So come talk with me.
I'm gonna come after.
No, that's not what I meant. So my Canvas shows that you're not.
Yeah, I just barely did it.
Oh, just barely.
Yeah.
Did you get the homework done?
No.
Not
I'm
yet.
gonna come after.
Okay. No, good job. You're okay.
Nope, I got it. Yep, I got it.
Okay. So mine showed that you weren't caught up in Canvas either.
Yeah, this morning I actually went in and I did all my AP classes.
Okay.
But, so yeah, that was the
Just
last.
making sure.
And then I
Very good. Good job, Ruth. Good work. Caitlin. Kate. Kate. Good job. Michael.
So I have everything in on Canvas, but it's not synced on Skyward yet.
Oh, we're good then. That's okay.
I have my number.
Did you get everything in to Canvas?
I'm still missing.
Missing one thing? Okay. I apologize. It was not my intention. So. Brain isn't that strong.
It's the right way. Say that. Yeah, talking about AP line. Yeah. He's like, no, I guess it's like, I don't even know what to talk about. Yeah, literally. Like, so like, one of the people you love was like, what is something that you have all the time?
Okay, look up, please. Look up. Okay, look here. Okay, I'm handing you another reference sheet. Look. 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 Okay, look at it close. Okay, everybody look. John, look up. Notice that this side is it's just a big table. Okay? Notice the other side is more of a variety of things. Okay? This side most people don't use, but I include it because I have found a few that found it to be helpful. The key is the side that's more of a variety. So what you're going to do, much of what is on this sheet you already have on the blue reference sheet that I gave you. So Harrison is proudly displaying the blue reference sheet and the sheet protector there. Rachel has it as well. Okay, pop that out for me, Anna. So much of what is here is also here, but this is a more condensed form. The idea being that now that we've learned this, we can kind of get the notes smaller. Does that make sense? Like you don't need as much detail once you've learned it. So what I would do is I would take this pink sheet, and I would put it on the same sheet protector. I would put it so that the note side, not the table side, is showing. And that way you have a very nice reference sheet for everything we've learned in this unit so far. Does that make sense? Okay, cool. You're welcome. There's two of them. You're welcome. There's a bunch. Please hand those and then give me the extra. They wouldn't separate, Paisley, so. So Michelle's busy, so we'll help her. There we go. There's two, there we go. There's three, I believe. Hand one to Haley for me. You're welcome. There's one for her. You're welcome. There's one for him. There's two. That should be two, maybe three. Three. Hand one to Kate right behind you there. Send it to, there we go. You're welcome. Okay, look up. Okay, None today. Thank you. I don't have any today. Okay, the gold, the green, and the purple packet, they do feel a little bit like busy work because they feel kind of repetitive. I apologize for that. They have to be somewhat repetitive because I'm trying to get you to see how things connect and the connections between one graph and another. So make sure when you do the purple, you again don't just do it. Like you pay very close attention to the following details. Make sure you know exactly when you're talking about position versus velocity versus acceleration. Make sure you are keenly aware of the difference between a y-coordinate on a graph and a slope on a graph at that point. From this day forward, we have to pay attention to both because they have related but different meanings. Also pay attention to this idea. Right here, just say it out loud as a class. Is that y-coordinate positive or negative? Say it. Negative. But the slope right there, the tangent slope at that point, is that tangent slope positive or negative? Say it. Positive. So you've got to be paying attention to the details. Am I talking about the y-coordinate of the velocity, or am I talking about the tangent slope of the velocity? As soon as I say tangent slope of the velocity, your brain has to say, oh yeah, that's the same as the acceleration. So that green slope, whatever value that green slope has, that will be the exact same thing as this y-coordinate right here. So that y-coordinate has the same value as this green slope. Questions, please. 2 points for Kate. So tangent slope is the slope at one point, like exactly that point. Now remember, the word slope means rate of change. So this green slope, whatever that slope is, that's how fast the velocity is changing at that moment. Like the curve is fairly steep, so we know the velocity is changing quickly. Secant slope is a slope between points. So if I go from here to here, okay, that slope tells me how the velocity is changing on average from one point to another. That means that secant slope is an average acceleration. Does that help, Kate? Okay. Anybody else? Okay, those are the key things. Really, that was a really good summary. Got to keep track of which graph. Am I talking about a y-coordinate or am I talking about a slope? Am I talking about a tangent slope or am I talking about a secant slope? The other one that gets people mixed up is this. You all just said that this y-coordinate here was negative. Say it out loud, please. This y-coordinate, positive or negative? Negative. From this y-coordinate to this y-coordinate, did the y-coordinates increase or decrease? Say it. That was weaker, but increase is the correct answer. They went up. When the y-coordinates go up, they are increasing. It doesn't matter that they're both negative. Increase means they go up. Okay? Questions? The common life example that helps me remember that is if I told you the temperature changed from negative 20 degrees to negative 5 degrees, would you say the temperature increased or decreased? Say it. Increased. It's that simple. Okay? It's how it always is. Questions? Awesome. So key on the purple is, even though it's going to feel a little redundant as we work on it, you got to pay attention strictly to those details. That's the whole idea. So here we go. Oh, one other thing. I do want to eliminate as much busy work as possible. And I noticed when I was kind of working on this worksheet that when I'm on this page, the second page in, I got very annoyed with the fact that as I was trying to answer questions, I kept having to look back at the graph or look at my calculator. I'm like, this is just getting to be a pain. So I didn't want it to be busy work. So I want you to remove the last sheet from the packet. And that way you can have this sheet in front of you as you are answering the questions. Therefore, you don't have to flip back and forth. It's right there. And you don't even have to use your calculator on this one. For example, we talked about last time how to find this number. That number is simply the 0 of the red. So we learned how to do that, so I didn't feel like you had to keep doing it over and over again. I've never seen a student that needed to practice that. That's, once you know it, you know it. It's not hard. So you don't have to use your calculator on this packet. You can just use the graph I gave you. So, questions? Cool, let's go. It says, use the position graph. So I look at the blue to determine that the particle's position is decreasing from time equals 0 to time equal what? So you're looking at the blue graph and you're going to raise your hand and tell me, at what time does the particle's position stop decreasing? Hands up. At what time does the particle's position stop decreasing? Now, huge hint. If I am looking at position and I'm trying to understand position, then I'm focused on y coordinates. So I'm looking at the y coordinates of the blue, and I'm trying to understand what those y coordinates tell me. So I'm looking at these y coordinates. So say it out loud. Each of those y coordinates is positive or negative. Say it. Negative. That's telling you that this particle is, for all of those different times, it is on the left side of the origin. The negative says the particle is over here on the left. Those y coordinates are becoming more and more negative until I get to here. They don't get any more negative than this y coordinate right there. Then they become slightly less negative. So hands up again. What is the time when the particle stops going, what is the time when the particle's position stops decreasing? It's like temperature. When does it stop decreasing? Kate Crofts. Okay, listen carefully to my question. Raise your hand if that makes perfect sense to you and you knew it. Point. 2 for Kate. Please, Chris.
What if it stops increasing at 0.202 plus if it went down?
Oh, awesome. Good question. 2 for Chris. It's not really easy to see. You'd have to zoom in closer. We did it in a previous discussion. That's why I didn't stress too much about it. It actually doesn't. It doesn't ever get flat. It just keeps going down just very, very slowly. But you are correct. From this picture, it's not clear that you could see that. If this were a test question, I would take my calculator and look closely. I would look closely like in this vicinity. Come on. This area here, to make sure that it was doing what I thought. Does that answer your question? 2 points. Anybody else? Keep going. Okay. Every time you see the word therefore in this packet, it's asking you to see a connection. So we're trying to associate what's happening to the position with what's happening to the velocity. And you have this in your notes now. You have what's known as Danica's chart. That's this thing up here, named after the student Danica Wright. Okay, soccer player, by the way. Yeah, she actually played for the University of San Antonio in college. So that chart tells me the following. It says, if your position graph is going down, okay, look here. If the position graph is going down, that means every little slope, every little tangent slope on that position graph, say it out loud as a class, is the slope of each of those green lines positive or negative? Negative. Now the slope of those green lines is negative, not because the black dots are negative. The slope of the green lines are negative because the curve is doing what Chris just said, the curve's going down. So Danica's chart summarizes that. It says, hey, your position graph is going down, then every y-coordinate of your velocity graph must have a negative value, because the y-coordinates of the velocity match the tangent slopes of the position. So, sure enough, look, here are the y-coordinates of the velocity. This y-coordinate is negative because this tangent slope here is negative. This y-coordinate on the velocity is right here, negative, because this y-coordinate of the position, this tangent slope of the position is negative. Questions? 2 points for Soraya for nodding. Any feedback is very appreciated. So therefore, the velocity graph is negative from time 0 to the same time. This is where the worksheet feels a little repetitive, but that's on purpose because you're supposed to see the connections. Questions? Cool. Therefore, the particle's moving left. If my velocity is negative, particle's moving to the left. Questions about anything? Move on. Item 2. The position graph is increasing from time equal blank to time equals 7. Raise your hand who knows what goes in the green blank. Rachel? So same spot. Ends up, who knew it? Point, 2 for Rachel. Therefore, hands up, what goes in this red box here? Hands up. Let's go, Riley. Therefore, Danica's chart again, when the position graph is increasing, the y-coordinates of the velocity must be positive. So this is positive for that same time period. Who knew it? Point, 2 for Rachel. Questions so far? Okay, keep going. Okay, new idea here. If you look at your new reference sheet, one of the definitions is for what's known as a relative maximum. Okay, find that. Now, warning to everyone. Every year I tell the class, this is the definition for a relative maximum. And then every year, some number of students will miss a question on the test because they invent some other definition. It seems funny, but it's true. Like, really, like I say, this is the definition. And then they'll answer it wrong and say, why did you pick that? Well, because a relative max is this. I'm like, where did you hear that? Like, they just come up with something else. So memorize the definition on the pink sheet. The definition is, any function has a relative or local max when that same function changes increase to decrease. So any function has a relative or local max when that same function changes increase to decrease. So, right here, the position graph, that's the function, has a relative, you can abbreviate, or local max, you can abbreviate that, at that time. Because that's, oh sorry, that would be min in this case, my apologies. Max and min, same idea. So this would be a min. So right here, we see the position graph changing from decreasing to increasing. So this is the time when the position graph has a relative minimum. That's the only definition you should memorize. Don't memorize other definitions. Questions? Cool. Here's the correspondence. Oh no, sorry, different definition. So also on your pink sheet, there's this one here. Memorize this. Any function has a critical point when the tangent slope of that function is either 0 or undefined. So right here, at this time, the tangent slope right there is 0. That means the position is not changing at that moment. That exact moment the particle is stopped. The position is not changing. The particle was doing this. It was moving left because its position was getting more and more negative. More and more negative, more and more negative. Then at exactly 4.848 seconds, I don't move anymore. And then in the next instant, I start going the other direction. So for one instant, my position is not changing. Slope means rate of change. So the rate of change of the position right there is 0. When the tangent slope of the position is 0, the position has a critical point. So write that in. Okay. One of the biggest mistakes on the test is just not being specific enough. Like, I'm talking about the position having a critical point at this time. Now, I can determine that by looking at the velocity, because the y-coordinate of the velocity is the tangent slope of the position. Therefore, when the tangent slope of the position is 0, the y-coordinate of the velocity, the y-coordinate, this is v, the y-coordinate of the velocity at that same time must be exactly 0. Like that. Questions about anything? Please, Rachel. Yeah, the handwriting there is not the best. So I'll say it and then I'll point what I wrote. What I said was, are you okay, Rachel, that this position graph has a critical point at this time because the tangent slope on the position is 0? Awesome. Are you okay that this tangent slope on position equaling 0 means that when I go to the velocity graph at the same time, I have to find a y-coordinate whose value is 0. So that's what got written here. Right, it's kind of squished in there. I apologize for that. So it's v of 4.848. That must have a value of 0. Does that make sense? It's good work. So Rachel gets a full ticket for this one. One of the key things in this class is just persistence. It's like saying, hey, wait a minute, I don't see it. And then we just be persistent enough to talk long enough that it really clicks. It's well done. Anybody else? Please.
How do we know if you write a relative minimum or if you write critical points? Because they both start with the same.
Gotcha. All eyes up here. Listen to Maddie's question. She said, how do I know whether I'm supposed to say that I have a local min or a critical point? Here's the difference. So, 2 points for Maddie. Someone else raise your hand and just tell me, what is the definition for a local min? You can read it, I don't care. What is it, Michelle? Okay, so any function has a local min when that function goes decreasing to increasing. So this would be a local min. 2 points for Michelle. Point for the whole room. Is this spot, okay, sorry, one person, raise your hand. I need somebody to read the critical point definition. Don't care who it is. Hey, John, what is it? No, sorry, critical point, critical point. You're good. Just read off the reference sheet. It's at the very top. There we go. Stop right there. That's good enough. That's good enough. So here's our function. We know that there's a local min at this point because, as Michelle said, 2 more for Michelle, this function is changing from decrease to increase at that point. John said a function has a critical point wherever the tangent slope of the function is 0. So hands up. Does this function have a critical point at the same spot? Actually, this is the dumbest question ever. Just say yes or no as a class. Say it. Yes, it has a tangent slope right here of 0. Sorry, that was bad. So as Maddie said, this function has both. It has a local min at this point. It also has a critical point at that point. Here's a case where they're different. If a function does this, raise your hand this time. Is that function changing from increase to decrease? Raise your hand. Just yes or no. Hands up. Hands up. Is that function changing from increase to decrease? Yes or no? Let's go Hannah. How many agree? 0.2 for Hannah. This function is not changing from increase to decrease. Therefore, this function does not have a relative min. It doesn't have a relative max either. Raise your hand and answer yes or no. Does this function have any places where the tangent slope of the function appears to be 0? Looking for hands? Question. Who agrees? 0.2 for question. Right here. So this function has a critical point, but it does not have a relative min or a relative max. Does that answer your question? Kind of. So really, they'll interchange them, but they'll be specific as to what they want you to identify. A very common thing on the written section of the AP test is to do this, Maddie. They give you a function, and they say, please identify the critical points of the function. And so you have to identify a point like this and a point like this. Then the next question will say, identify whether each of those critical points is a relative min, a relative max, or neither. And that's where you would have to say, oh, the first point is a relative min, but the second point is neither. Does that answer your question? Okay. Anybody else? Please, Michael. Everybody look at me. The way to memorize it is this. A relative min or a relative max will always be also a critical point. However, a critical point won't always be a relative min or relative max. Yep. Anybody else? 2 for Michael. Okay, cool. Next one. Okay, hands up. What goes in this line here? Show me your hands. What goes there? Quick. Red line. The velocity graph is increasing from time 0 to time blank. Looking for hands here. Most people. Few still not. Let's go Spencer Olson. So let's follow the velocity graph here. No worries. So almost 6. Let's follow. So you're making an error, so I just want to help you see the error. Is that okay? So here's velocity right here. When we say is the velocity increasing, that means we want to pay attention to what the y-coordinates of velocity are doing. So from here to here, Spencer, do the y-coordinates of velocity increase or decrease? Then to here? To here? To here? To here? Very good. So the velocity graph is increasing up to this point. Does that make sense? 2 points for Spencer. Please raise your hand if you knew it. Who knew it? Come on, who knew it? Hands. Show me. I got to see how we're doing. Point. Questions. Please, Isaac. Actually, let's go with Isaac's question. So everybody raise your hand and answer this. We have clearly identified that up to 0.202, the velocity is increasing. Isaac has correctly identified that there is another time period for which the velocity is increasing. Hands up, what's the other time period? Come on. What's the other time period when the velocity is increasing? From when to when? From when to when, Dallin? Forevermore. So, starting here, the velocity is increasing again. How many knew it? 0.2 for Dallin, 2 for Isaac. Does that answer your question, Isaac? Anybody else? Hannah? Oh, gotcha. No special reason. It just, the worksheet was written that way. It truly is increasing from prior to that as well. Yeah. Yeah. On a test question, they'll make it clear as to what you're supposed to be focusing on. So no stress there. Please. 2 points, Hannah. The number right here? Gotcha. So all eyes, come on, 2 for Luke. Last time we showed, if you forgot, it's okay. We showed how if you do the second trace and choose, as Terrence's saying, maximum, then you can do left bound, right bound, and find it. Yeah. 2 for Terrence. Anybody else? Okay, all eyes up here. Everybody, look at me. Okay, listen to what Luke just asked. Here's the other way you can find that time, right here. And the way I'm going to tell you now is much more common. Like you'll use this method much more frequently than the maximum method. It's because of how acceleration and velocity are related. When the velocity is going up, okay, this chart is all about y-coordinates. The x-coordinates are just time. So this chart's all about y-coordinates, and you always read left to right. So when we see y-coordinates that are going up, we are guaranteed that the y-coordinates of the acceleration will be positive. And you can see it. Just like Hannah said, all of these y-coordinates are positive. That means for all of this time, these y-coordinates on acceleration being positive tell me that the velocity y-coordinates are going up. And Danica's chart summarizes that. Y-coordinates of acceleration being positive, I know y-coordinates of velocity go up. Questions? So back to Luke, that means if I want to find this time, I can find the zero of the acceleration. The zero of the acceleration will give that exact same time. That's what this next line is saying. Therefore, the acceleration graph is positive from time equals 0 to time equal 0.202 again. Question? Sweet. So, number 4. Hands up, please. Tell me what goes on this blue line right here. Hands up. There we go. We get somebody new this time. Let's go, Parker. The acceleration graph, the velocity graph is decreasing from this time until this time. Hands up, who knew it? 0.2 for Parker. Question? Oh, please, John. I think I know the mistake you're making, so I'm going to tell you what I think. If I'm wrong, you tell me I'm wrong. You with me? When it says, so here's, look everybody, here's the key. You've got to identify the correct graph. We're good there. We're looking at the orange, yes? No worries. I'm going to keep talking now. You got me started. So you got to look at the right graph. We're looking at the orange graph. Second thing is you've got to pay attention to, am I supposed to be thinking y-coordinates? Am I supposed to be thinking slope? Well, when it says velocity is decreasing, that means y-coordinates. So as I look at the y-coordinates of the orange, They are negative. They continue to become more and more negative until I get right to there. So this is the portion of the velocity graph where the y-coordinates of the velocity are definitely becoming more and more negative. Did that answer your question? Okay. 2 for John. Anybody else? Cool. Therefore, so it's Danica's chart again. If my velocity graph is decreasing over some time period, then the acceleration graph must be, say it out loud, what is it? Negative for that same time period. Now again, that really means two different things. That means if you look at the y-coordinates of the acceleration for this time period, look, the y-coordinates of the acceleration, all of these y-coordinates on the red must be negative, and they are. But it also means a y-coordinate of acceleration is the slope of the velocity. So that means that all of these tangent slopes on the velocity must also be negative. Okay, question? Cool, keep going. Okay, the velocity function, so we talked about this point here where the velocity is switching from decrease, actually it's right here, from increase to decrease. Therefore, the velocity function has a relative or local max Oh, good call. 2 for Taryn. You can actually use either word and it's 100% acceptable. So on a written section, if you write local, fine. If you write relative, fine. You don't ever have to write both. On the multiple choice, they will switch back and forth. So you just have to recognize that they'll use either one. So, anybody else? And notice in your reference sheet, there's a definition for relative extrema. The definition for relative extrema is very easy to memorize because relative extrema simply means a relative min or a relative max. So it's just either. So not a new definition, it's just either of the other. So, questions? Keep going. If the velocity function has it, this is Maddie's question, and also Michael's. If the velocity has a relative max right here, then we know that the velocity also has a critical point right there. And the critical point of the velocity is exactly the same place where the acceleration has a y-coordinate of 0. So again, the packet is all about how things associate with each other. So, questions? Sweet. Next one. The acceleration graph is blank from time equals 0 to blank time. So they're talking about this little window right here. Oh, actually, we're going on to a slightly new idea. We're over here on acceleration. We're talking about this little section here of the acceleration. And we are noticing that in that section, the acceleration is decreasing. Therefore, the velocity graph is concave down in that same region. And we can see it. It's a little tough to see. This graph blown up version helps. So here's where I see the acceleration y-coordinates going down. Therefore, the y-coordinates of the velocity graph must have a concave down shape. Like that. Questions? Please.
How do you know when it says, so it says the acceleration graph is blank from time equals 0 to time equals 1. How do you know where that is?
I'm going to pay Luke a ticket for this one. This is where the packet is not as clear as it really should be. The whole idea of every question in the packet is for you to see how things correspond to each other. So I really can't answer, that's why I'm giving you a ticket. It's a really good observation. I can't answer this one without really reading this one. Because they're asking you to see how they correspond. They want you to see, hey, there's something about acceleration that corresponds to velocity having some concavity. And so that's where the chart is super useful, because I can look here and go quickly, okay, wait a minute. The concavity of velocity is related to the up-down of acceleration. And that's how I could make the conclusion. Does that help? Yeah, it's a good question, Luke. Please.
Why are we saying 0.02 instead of 1.1?
Oh, I'll pay a ticket for that. That's also not perfectly clear from what's in front of us. You actually have to zoom in to see it very well, so the worksheet's a little flawed there. If you zoom in closely like this, you notice that the velocity is, hold on a second. Oh, hold on. I apologize. No. Ticket for sure. Yeah, I misread it. Harrison got it perfectly. Well done. Yeah, look what he said. It's perfect. Watch. Yeah, I just totally misread it. Here's acceleration. Acceleration is decreasing all the way until right there. And similarly, like we said to Luke, the velocity graph is definitely concave down all the way to there. Is that what you meant? Yeah, much better. Raise your hand if you noticed that error that I made. I'll pay. 2 points. Good work. Anybody else? Oh, please. It does work. Yeah, it does work. It's not technically wrong. It just is a better answer to go further. But that's where the worksheet is somewhat flawed. I totally agree. Yeah. You needn't worry about that type of a flaw in an AP question. They'll make it much more precise. So, anybody else? 2 for Isaac. Okay, number 6. Okay, new definition here. It says the acceleration graph is blank from blank to blank. I think based on our conversation now, you should be able to do a much better job than I did of filling in those 2 blanks, because we're trying to see how the acceleration graph corresponds to the velocity graph's concavity. So hands up if you know what goes in those 2 blue lines. Do it with me. So what goes in the top 2 blue lines right here? You're trying to see how the acceleration is going to correspond to the concavity of the velocity. So what goes in the 2 blue lines? Hands up. There we go. Hoping for a couple more. Still hoping for a couple more. Couple more, Katie. Oh, let me help you. So we're looking here. We're comparing acceleration to the concavity of velocity. Does that feel good to you? Okay, so tell me, Katie, what characteristic of the acceleration corresponds to the velocity's concavity? I said it badly. the velocity's concavity is here. The acceleration's kind of up-downness, increasing versus decreasing. That's what corresponds to the velocity's concavity. Does that make sense? Because that's where the velocity graph is concave what? Up. For that same, does that make sense, Katie?
Yeah.
Awesome.
Like 2 to 1.
Don't worry. Okay, please raise your hand if you knew it before Katie said it. Point 2 for Katie. Anybody else? For some reason I want to say sands, but it's rands. Yeah. I don't know why. So, anybody else? Cool. All right, new definition. Again, memorize the definition on the sheet. Don't create your own definition. Any function has an inflection point when that function changes concavity. Any function has an inflection point when that function changes concavity. So the velocity is changing concavity at this time. Because the velocity is concave down, and then exactly at 1.750 seconds, the velocity switches to concave up. Please.
That point, like the between the concave down to concave up, already happened when the acceleration and velocity, like intersect.
Oh, listen to Maddie, 2 points. The intersection here is pure coincidence. So don't count on that at all. No, good question. Now there is a correspondence. It's here. It says velocity has an inflection point. At this time, because the acceleration is changing. Look over here. It's what Katie said. From, in this case, the acceleration is changing from decrease to increase at that same point. So it's not the intersection that's important. What's important is here's acceleration decreasing. Now acceleration is increasing. That switch is when the velocity's concavity will change. Questions? Please, Kate. I'm going to pay a ticket for this one. So the definition of concavity is actually in Danica's chart. So here's how you read the definition. Remember, okay, look here, everybody look. Remember that the slope of the position is the y-coordinate of the velocity. So if the y-coordinates of the velocity are going up, okay, that means the slopes of the position are getting higher and higher. When the slopes of the position increase, a curve is known as concave up. That's the definition of concave up. If the slopes of the position are increasing, the position curve is concave up. We don't use that definition too heavily. We more do it just kind of visually. And here's the quick visual definition. Here's a curve. Look, any curve that has this sort of shape, or any part of that shape, is considered to be concave up. So here's a curve that is concave up because it has part of that shape. It doesn't have to go back down, just having part of that shape, concave down. How many saw the error? There you go, 0.2 for Riley. Okay, question. Sorry, Riley. Please.
So is the reason why this is an inflection, okay, so if this were a velocity graph, how do you know whether it has like a maximum minimum or?
This one here that I grew, right here.
Does that make sense? Like, no, the one back, so like we call it an inflection point, or isn't it also like a minimum?
Depends on which graph we're talking about.
Yeah, so that's what I'm saying. Is it only, we only call it, like, because I know inflection point applies to like any of the graphs, and this maximum only apply to velocity graphs.
Oh, good question. Everybody look. I'm paying Kate in a second. Watch. So if you look at the definitions, they say specifically, any function has a relative max. That means any function can have a relative max. It's good so far? Okay, it also says any function can have an inflection point. So let's just practice together here. Let's finish this, and then we'll practice. So the acceleration is changing from decrease to increase. Is everybody okay with if I erase everything now? Can I erase? Okay. So think of the definition. It says any function has a relative, we'll do relative min, when that function changes from decrease to increase. Raise your hand if you can tell me, where does the position graph have a relative min? Hands up, hands up. I want everyone you're doing great. I just want everyone to get it. Where does the position graph have a relative min? Relative min is when the graph changes from decrease to increase. Where does the position graph have a relative min? Let's go, Chris. So please raise your hand if you would have answered that time. Point 2 for Chris. Stay with me. Oh, sorry, 1 second. Go ahead, please. My bad.
Is the reason why it's not a relative min is because since it's like all the y coordinates of that acceleration are negative, so they're taking as an increase decrease. It's just concave.
Oh,
That was my question.
gotcha. Let me try again.
Okay.
So Taryn is making the mistake that is often made on a test, so now is the perfect time to fix this. We just said that the velocity has an inflection point at this time because that's the time when the concavity of the velocity changes. That is exactly the same time when the acceleration has a relative min. So the acceleration doesn't have an inflection point at that time.
Okay, so acceleration having a relative min.
When the velocity is having an inflection point. But Danica's chart summarizes that for you. Because look, when the acceleration changes, decrease to increase, that means acceleration has a relative min. That is going to be at exactly the same time that the velocity will be changing from concave down to concave up. That's how you read the chart. Does that help? So answer this, everybody. 2 for Taryn. I want to find the exact time when the position has an inflection point. Raise your hand and tell me. What is the exact, there's actually more than one answer. I'll take either one. Give me a time when the position has an inflection point. Hands up, come on. Look at your definition. When it says any function has an inflection point when that function changes concavity. So what's the time when the position has an inflection point? Hands. Let's go, Lily. So let's go over here. So small error, 2 points for Lily though. Error is as good as a right answer as long as we understand it. So at that time, my position's concave up, and it still is concave up. So throughout this entire region, the position is concave up, so the position is not changing concavity, so no inflection point there. No worries. Hands up. What's a time when the position has an inflection point? Lily. So at this time, the position is concave down. Now the position is going to switch to concave up. Hands up if you knew it. Point 2 for Lily. Please. Gotcha. Hands up. Who can see the other time when the position changes concavity? 2 for Rachel. What's the other time when the position is changing concavity? Marielle? Yep, right here. The position is concave up. Now the position is concave down. How many saw that one? Point 2 for Marielle. Did that answer your question, Rachel? Okay. Look at me. More important than that is this question. Please raise your hand and tell me, at what time does the velocity change from decreasing to increasing? Hands up. What is the time when the velocity changes from decreasing to increasing? What is the time when the velocity changes from decreasing to increasing? Trying to get somebody I haven't called on yet. Let's go, Julian. So I'm looking at velocity. So mistake, let me help you see it. You're good. Try again. So right here, the velocity is decreasing. Now the velocity is increasing. Now listen, okay, this is the key to the test. Listen to my words, not what I did. We looked at velocity. We identified where velocity did this. But we used that to find an inflection point on the position graph. It's exactly the same point. That's what they have you do on the test. They make you look at velocity, but you're finding an inflection point on position. Question? Please.
Could an example on like the test, like give you a velocity graph and then say what is the inflection point on the position graph so I can like understand?
Yep, that's the whole idea. A test question is not going to give you all three graphs. They're going to give you one. And so you won't even see what you're trying to identify because they want you to identify the unseen based on a correspondence. So if I'm finding an inflection point on position, but I'm looking at velocity, I'm not looking at velocity's concavity at all. I'm looking at velocity doing this because that will indicate position doing that. That's the idea. Two for Maddie. Questions? Please.
On the test, you got a question that's like, okay, and we're only given the acceleration graph, and it's like, where does velocity start increasing? You could look and see velocity increasing, and that means that acceleration is positive, so we can see where it goes starts being positive on the graph.
Yep.
With 3.29.
So here's exactly what you do. Look. Look. It's exactly what Taryn said. She'd say, okay, if I'm looking at acceleration, because that's all they gave me on the test, and I look at these acceleration y-coordinates, they are all positive y-coordinates. Right here, positive. That means even though I cannot see the velocity, I know the velocity is going up.
The point where acceleration is positive, no, it's the point where it's
Yep. Now look close again. Look, that doesn't mean the velocity is positive, just increasing. These velocity values are definitely going up. That's why I gave you the three graphs overlaid on top of each other as we're learning about it, so your brain can say, yeah, I can see it. I can see how they correspond, so I'm preparing myself to be able to answer the question when I can't see it. Does that make sense? 2 points. Anybody else? Awesome. Okay, so did we fill out all of 6? I can't remember. Okay, thank you. Go to 7. I'm not sure why I wrote that, but at some point in the past I must have had to leave for some reason. So, moving on. I think I was after school or something and I had to run to the office. I'm like, okay, I'll be right back. So, humor. Okay. It's not really very funny, but whatever. So again, the entire packet is all about correspondence. It's like I was saying to Luke, 2 more for Luke. We're talking about position. We're talking about the concavity of the position. We're trying to associate it with something about the velocity. That's what we're doing in this question. How do we associate positions, concavity, with velocities something? So raise your hand if you know what goes in the blanks. Come on. And we're kind of reading left to right because it said start at time 0. So we're on position. We're starting right here. We're paying attention to the position's concavity. So hands up. What do we got? There we go. Michelle. Please raise your hand if you would have said exactly what Michelle said. Keep your hands up for a second. Point 2 for Michelle. Please. Oh, for sure. Stay with me, Isaac. 2 points. The position graph is definitely concave up here, which means the velocity graph must be increasing during that same time period, which the velocity graph is. Does that make sense so far? It's just that the question said start at 0. Oh, hold on. Oh, hold on. I'll pay a ticket for that one. That's an error in the packet. That's well done. Yeah, Isaac is correct. This should say not 0. Right, Isaac? Yeah, that's dead on. That's perfect. How many saw that mistake? I didn't see it. 2 points. The homework is the purple. It should go pretty smooth. So good job, you guys. Bell ring in like a minute. Oh, I see what you mean. Yeah, I got to fix that. I like the worksheet in the sense that it's trying to help you see the correspondence. It's not always clear where you're supposed to be looking. So I'll pay you for that one too. Well done. Good job, you guys.